Now we discussed about the topic of integrator by using the op-amp device. First, what is integrator? An integrator is a circuit that produces an output voltage that is directly proportional to the input voltage signal over a specific duration. The output voltage V of t is equal to minus 1 divided by RC integration of 0 to t V input. This is the mathematical function of the integrator output circuit. The next integrator circuit key attributes. First, inverting configuration. The integration is inherently inverted mathematically due to the active inverting terminal path. The next one is time constant, RC. The product of the resistor and the capacitor establishes the scaling gain multiplier factor. The next one is cumulative storage. A feedback capacitor continuously stores charge to represent the integrated history. Next one is the structural configuration of the integrator circuit. First one is the input resistor, the second one is the feedback capacitor, then third one is the virtual ground. First, the input resistor R establishes a constant current path proportional to the incoming input voltage. The next one is the feedback capacitor. Feedback capacitor placed directly in the feedback path, observing the current to build a linear voltage ramp. The next one is the virtual ground. Keep the inverting pin at exactly 0 volts, preventing source interaction. This is the structural configuration of the integrator circuit. The next one is the waveform transformation of the integrator circuit. First one is the square to triangle. Integration, a steady DC level results in a continuous linear slope. The square wave alternates between positive and negative levels. The output ramps up and down sequentially. First one is a positive cycle, linear downward ramp output. Negative cycle, linear upward ramp output. Then the application is mainly it is used in function generator. The next one is the sine to negative cosine. Applying a continuous input voltage waveform across the cyclic phases, transforming the wave shape while altering coordinates. Then first one is the phase shift, introduces an exact 90-degree lag to the output signal. The next one is the frequency dampening. Higher frequencies encounter smaller overall voltage outputs as capacitor charge loops shorten. The next one is the differentiator by using the op-amp device. The differentiator output voltage is directly proportional to the variation of the input voltage. The differentiator output equation is V out is equal to minus R of capital C dV by dt. Then the inherent characteristics of the differentiator equation is sensitive to change, then direct proportionality, then high frequency gain. First one is the sensitive to change, produces zero output voltage when static DC inputs are maintained. Then second one is the directly proportionality. Output magnitude depends entirely on the speed of the input signal transitions. Then third one is the high frequency gain. Higher rates of the change yield higher voltages, attenuating sharp wave transits. And this is the differentiator waveforms, triangular to square, then sine to cosine, then square to spikes. First one is the triangular to square. Linear constant slope produces steady flat DC limits. Then sine to cosine, the continuous derivative yields a 90-degree phase lead. The next one is the practical stabilization. First one is the integrator DC saturation, then second one is the differentiator noise and gain. First one is the integrator. Then ideal integrators accumulate even microvolt offsets and input bias over time, causing the output to drift and saturate to voltage for rails. And first one is the solution. A parallel feedback resistor. The second one is the functional. A parallel shunt resistor limits low frequency DC gain, stabilizing voltage drift. And the second one is the differentiator over noise and gain. Ideal differentiators features gain that increases linearly with frequency, transforming high frequency ambient noise into massive output oscillations. First one is the solution. Series input resistor. A small resistor limits maximum high frequency amplification to keep the loop stable. This is the comparative study of integrator and differentiator by using the op amp. The number of parameters which we are considered to give the parameters. First one is the input component, second one is the feedback component, the third one is the filter characteristics, fourth one is the high frequency stability, then fifth one is the primary waveform maximum. First one is the input component. Input component is resistor. In differentiator, input component is capacitor. Feedback component is capacitor. In integrator, feedback component is resistor. In differentiator, filter characteristics. Low pass filter behavior in integrator circuit, high pass filter behavior circuit in differentiator circuit. And the fourth parameter is high frequency stability. In integrator circuit, highly stable. In differentiator circuit, high frequency stability is unstable because it amplifies noise and requires limit. The fifth parameter is primary waveform action. In integrator circuit, smooth waveforms. Suppose if we give square, it gives triangular circuit. But in differentiator, primary waveform action is sharpens transitions. If we give triangular waveform, the circuit gives square waveform. The next one is industrial applications. The integrated circuit and differentiator circuit is mainly used in PID controllers, then waveform shaping, then analog computing.